Welcome to today's lesson. We're going to talk about projectile motion today, which is motion involving any object near the Earth's surface where only gravity is acting, is the only force acting. It could be straight downwards. It could be a soccer ball, projectile vomit, it could be a gun, or I guess a rocket launcher kind of thing as well. So we're going to assume no air resistance with projectile motion. Any projectile motion questions, we do that. And we have to split up the motion into X and Y components. Okay, so here's a sketch here. We're just going to draw the trajectory or the direction of a ball traveling. And in blue, we're going to represent U as the initial velocity here. Now, this is what I'm saying about breaking it up into horizontal and vertical components. We can see here the horizontal, if we've got an angle of theta, the horizontal component of the initial velocity, ux, will always be u cos theta. That's a formula we must remember or be able to refer to. And similarly, in the vertical direction, the initial velocity in the vertical direction is always u sine theta, or the magnitude of the velocity times sine theta. Now that u is really important that we define that for every question. We always just work out ux and uy based on what we're given in terms of angle and initial velocity. Now what I'm kind of going to show you here is what is actually happening when we split it into horizontal and vertical components. If we view the projectile motion from the side, so looking kind of behind maybe a ball, we can see that it goes up, up and up, and it slows down as it goes to the top and then comes back down and speeds up. So this is saying that the acceleration is always downwards with the acceleration due to gravity, so it's always pulling downwards. If we look from the top straight down, we'll actually see the ball kind of go at a constant velocity, which also means acceleration is equal to 0. So you can see there in the green dots there, they're equally spaced, so it kind of represents it going at constant velocity in the horizontal direction. Okay, so equal steps there. So from that we can kind of say AX is 0, so the acceleration is 0 in the horizontal direction. Which also means the horizontal component of velocity is always constant. So ux, the initial velocity, will equal the horizontal velocity at any point in time. Another way we can say that, so using one of our SUVAT equations, we've got Sx equals ux times t plus the acceleration component, but we can delete that because the acceleration is equal to 0. So we get a simple formula, Sx equals ux plus times t, in the vertical direction, a key formula or key thing we know is the acceleration is always downwards or equal to g, or the acceleration due to gravity, which is in this case minus 9.8 because it's downwards, up is positive, so minus 9.8 meters per second. So here we can really just use a lot of SUVAT equations to define our projectile motion in the vertical direction. Okay, so in red here, we've just got some SUVAT equations replacing A with minus 9.8, and we've got some common SUVAT equations here. Okay, so some key parts of projectile motion include at the very top, it'll all be in the horizontal. There is no vertical velocity there at all, so V of y equals 0, which means the total velocity will just be the horizontal or ux. This is also the slowest point in the motion, so it gets to the top. Another way of thinking is the maximum potential and minimum kinetic, so it's the slowest at the very top. And also at the same level as where we started, or at equivalent horizontal levels, we can actually say that the vertical velocity is the negative of what it was on the other side, or the initial velocity. In the vertical component. We can actually therefore say, because of Pythagoras, the speed is the same, but the direction is kind of different in that sense. So it's got the negative theta angle, if you want to think of it like that. Okay, So that's a summary of projectile motion. Here's a little app based on, so using GeoGebra. I've defined here, what we can actually say is U is actually the most important part of projectile motion. Assuming no air resistance, U is the only thing, and obviously gravity as well, that kind of affects the trajectory of the motion. So looking here, we can increase U, the magnitude of U, which is U mag, or the angle, which is theta there. And that's the only thing that affects the actual motion or the trajectory there. Turns out if we make theta 45 for a given U mag, or magnitude of U, it's maximum range, it'll get its maximum range. Okay, so looking at this here, this is an example. Let's have a look at Vy here. Vy goes from up and it gets increasingly downwards and downwards as it passes through. At the very top, you would have noticed that V of y is also 0. Let's have a look at another trajectory here, a little bit flatter. You can also notice in green, Vx is always the same. And you can notice that the horizontal component of velocity is always constant. Okay, so here's the last video. It's kind of a steep one. As you can see, when we get to the very top, that blue vector is at its smallest, so it's slowest at the very top, and then it speeds up on the way down. It actually takes half the time to get to the top to then get back down to the bottom. Okay, so I'm going to summarize a few other points here as well, just to end the video. The previous SUVAT equations we should use to find out the time, the length, the height, or the velocity components. But you might want to find the velocity at a particular point. So here's how we do that. We kind of actually just use a little bit of trigonometry and Pythagoras. So if we want to find the magnitude of the velocity vector, so V there, we actually just use the square root of Vx squared and Vy squared, which is just Pythagoras theorem. And then we use tan or inverse tan, arctan, to find the angle theta. So tan minus 1 of Vy on Vx. A few other hint formulas that you can use, some really useful formulas to find the max height. I won't go through the derivation. You can find the time to get to the maximum height, which is just going to be u sine theta, or the magnitude of the initial velocity, sine theta, on the magnitude of g, so positive 9.8. You can also work out the maximum height, so I've written that as sy at max. And that'll be u squared sine squared theta on 2 times the magnitude of g. Now, if you want to find, this is kind of the range formula, or finding something at the same level as it was at the start. Often use this, say, for a ball that travels a certain distance or that kind of thing. The time to get to the same level is just double the time at the max, so that's 2u sine theta on g. And this range formula, or Sx at the same level, R for range there, you can actually find out through the quick formula of u squared sine 2 times theta on g. Okay. Thank you for watching today's video on projectile motion. It was a fairly kind of quick video, but hopefully take down those formulas, go back through this a bit slower again. And please subscribe. It's really sincerely appreciated if you subscribe to this video, and definitely add some comments in the spaces below. Cool. Catch you later.